Hi, ladies. So, Chapter 13 covers intermolecular forces. Your Chapter 13 handout starts with the definition of intermolecular forces. They're the attractive forces that exist between molecules, and we have three that we're going to be looking at. In Chapter 13, they are London dispersion forces, dipole-dipole forces, and hydrogen bonds. So the next thing in our chapter handout, we're talking about intermolecular forces that we see, can actually see like happening between our molecules. Surface tension is the first one that we're going to be looking at. So this is the attraction between the surface molecules in a liquid. Surface tension is responsible for the formation of spherical droplets. So all of the surface molecules want to be holding hands as much as possible, and they're going to hold hands tightly. So that is going to form a sphere to minimize the surface area as much as possible. We can also think of it as the resistance of a liquid to spread, because those surface molecules are holding each other back, not wanting to let go. So that is surface tension. Our next definition that we're going to be looking at is viscosity. So viscosity is different than surface tension. This is the resistance of a liquid to flow. And these are due to strong intermolecular forces, and we'll talk about those a lot more in Chapter 13. Our examples of things that have high viscosity: motor oil and maple syrup, so honey as well. So we have a relationship here. As we heat up a substance, so let's take, for example, honey. You have honey in a jar, and you're trying to get that last little bit of honey, but honey flows really slowly. You don't want to wait a while to get the honey out of your jar. So if you put it in the microwave for 5 to 10 seconds, we're heating up that honey, and that's going to break apart those strong intermolecular forces between our molecules. And that's going to make it so that our viscosity decreases. We're going to flow a lot faster. So things like honey, maple syrup, motor oil, they have high viscosity. Things like water, rubbing alcohol have really low viscosity. So viscosity, resistance of a liquid to flow. Let's look at example number 1 in our student handout. So describe why a person using great care can fill a glass with water even above the brim. So I want you to pause the video, write down an answer, and let's see if we get the same answer. All right, so hopefully you actually did that. But so basically the intermolecular forces between water molecules, so our hydrogen bonds, we'll talk about those, are strong enough to stick the water molecules together to a certain extent. So our water surface molecules are going to be holding hands like really tightly. And to a certain extent, they're going to keep holding hands until the water molecules, the internal water molecules not on the surface, are going to push them enough that they have to break hands and gravity takes over and they spill over the edge. But basically, we can fill the glass over the brim with water because of surface tension between water molecules. Okay, example number 2. Which is more viscous, motor oil or gasoline? And describe the effect of temperature on viscosity. So I want you to pause the video, and then we'll talk about it in just a second. All right. So motor oil is more viscous. So maybe you have changed the oil in your car, or at least hopefully you do that once in your life so that you know how to do it. But oil is typically pretty thick, very viscous. It flows slowly. Gasoline, we're going to talk a little bit more about gasoline in a little bit, but it flows really, really quickly. So definitely motor oil is our more viscous, and like we talked about earlier, up here, as temperature increases, it causes the molecules to move more. So we're adding kinetic energy, heat energy, and we're breaking apart those intermolecular forces between our molecules and breaking them away from other molecules. So they get to flow a lot faster and easier. Okay, next thing on our chapter handout, we're talking about vapor pressure. So, vapor pressure, let's look at the second part of this definition because it makes a little bit more sense. And then we'll add the first part. But vapor pressure is the pressure exerted by gas molecules above a liquid. So we have a glass of water, and there are water molecules in liquid form in the liquid, and then in gaseous form above our liquid. So water, as we know, evaporates. So those liquid molecules are evaporating, and eventually when we get too many liquid vapor molecules above our liquid, those gas molecules are going to stick together, which means they're going to change back into the liquid phase. So there's just like this constant cycle of liquid to gas that's happening in a closed container with a liquid and a gas in. And so vapor pressure is the pressure exerted by gas molecules above a liquid when the rates of vaporization and condensation are equal. So we have the same amount of molecules evaporating as we do condensing back into a liquid. So vapor pressure, if we have a high vapor pressure, that means that our substance evaporates very easily. Like those molecules in our liquid aren't really holding hands very tightly. So these two water molecules, one of them can easily just go up and be a gas. They're not holding hands tightly if we have a high vapor pressure. We have a lot of gas molecules because we are evaporating easily. If we have a low vapor pressure of a substance, that means our water or our liquid molecules are holding hands pretty tightly, and they don't want to let go of their friend so it can go be a gas. So they're going to stay liquid molecules as long as possible. So if you have a low vapor pressure, we don't have very much gas up above our liquid, hence the gas pressure is low. Our next thing that we're looking at is volatile. So volatile means that a liquid evaporates easily. So it has low intermolecular forces. Our examples are rubbing alcohol, acetone. Maybe you've spilled a little bit of acetone on your counter, and if you waited like a minute or two, that little puddle would evaporate really easily. So rubbing alcohol and acetone evaporate a lot faster than like water, and especially oils. So here's two relationships that we're going to look at. So high vapor pressure means that we are evaporating quickly. Our substance evaporates fast. Sorry, that was for vapor pressure, not volatile. And low vapor pressure, that means our substance evaporates low. So volatile, something evaporates easily. We have low intermolecular forces. That means our two molecules are not holding hands very tightly, and they're okay if their friend goes and be a gas. All right, so let's look at example number 3 next. So 1 milliliter of water is poured onto one hand, and 1 milliliter of acetone is poured onto the other hand. As they evaporate, they both feel cool. Which one feels cooler and why? So I want you to think about that for a second. Pause the video, write an answer down, and let's see if we get the same answer. Okay, so acetone is more volatile compared to water. It evaporates faster. That's what volatile means. So if something is evaporating faster, that means it gets to take more of your heat that you are releasing through your skin. It's taking more of the heat in your skin and taking it away from you, which is why it feels cooler. So the absence of heat is going to feel cool for us. Similar to sweat. So sweat's going to evaporate off of us, and it's taking heat with it. So that's how sweat cools us down. So same thing here. Acetone's evaporating faster, so it's going to take more heat with it, hence why it feels cooler. Fun things to think about for sure. All right, example number 4. 2 samples of water of equal volume are put into 2 dishes and kept at room temperature for several days. The water in the first dish is completely vaporized after 2.8 days, while the water in the second dish takes 8.3 days to completely evaporate. What can you conclude about the two dishes? So pause the video, write an answer down, and let's see if we get the same answer. All right. There's a few things you could think of. We're going to assume for this question that our dishes are made out of the same thing, like ceramic dishes, might as well. So that would mean that maybe our dishes' shapes are different. So if we have a really wide, shallow dish compared to something that maybe looks like a test tube, or like a vase, if you want to think of it like that, we have a lot more surface area on a really shallow, wide dish, and a lot more opportunities for those surface molecules to evaporate into a liquid. As opposed to like our test tube or vase looking thing, we have like barely any surface area for that liquid to gas interaction, for those liquid molecules to jump up and be a gas, and to gain that energy in order to do so. So if we have less surface area, that means we're going to take longer to evaporate. So we have a longer evaporation rate. So shape of our dishes is what we're looking at there. Okay. So we have a few relationships here that we need to remember. So rate of vaporization, so how quickly something evaporates, increases with increasing surface area. So our two dishes, so this dish here, the really long open one, is going to evaporate a lot faster than like our vase or test tube looking thing. Increasing temperature, so the temperature, the heat, is going to cause our molecules to move faster, breaking intermolecular forces between molecules, which means that the liquid molecules are going to let go of their friend, who's going to go be a gas molecule, a lot easier. And then decreasing intermolecular force strength. So if we don't have a really strong hold between two molecules, they're not holding hands really tightly, then they're easily going to let their friend go to be a gas. Okay, so we do need to know those relationships there. Okay, so example number 5. Consider the following properties of liquids. State whether the value for each property is low or high or low for the liquid with a strong intermolecular attraction. So strong intermolecular attraction, think of your molecules holding hands really tightly. So I want you to answer A through D, pause the video, and then let's see if ours match. All right, A, vapor pressure. If we have strong intermolecular attractions, our liquid molecules are holding hands really, really tightly. They don't want their friend to go off and be a gas. Vapor pressure, we are measuring the gas pressure above our liquid. So if our liquid molecules are holding hands tightly, that means we have less gas molecules that are going to be let go to be gas molecules. And hence our gas vapor pressure is going to be low. We don't have as many gas molecules above our liquid. Boiling point is going to be high. Boiling point is the point where a liquid turns into a gas. So if we have strong intermolecular forces, attractions, that means we have to put a lot more energy, heat energy, to break apart those intermolecular attractions to get our liquid into the gas phase. So high boiling point because we need more energy. If we have strong intermolecular attractions, our viscosity is going to be high. So if we have a molecule here and its friend is next to it and they're holding hands really tightly, we don't only have to move this gas molecule, we have to move the other gas molecule as well if we're flowing. So they have to move together because they're holding hands really tightly. Now imagine that with like tons and tons of molecules. It's going to be a really slow energy requiring process. So viscosity is high if we have strong intermolecular forces because we have to move all of those molecules really slowly. So think of like moving honey molecules, those sugar molecules. They're bigger and they have stronger attractions, which means they got high viscosity. All right, and then letter D, surface tension would be high. So The surface molecules, they're going to be holding hands tightly, and they don't want to let each other go. So our surface tension will be high. So think of it like water. So water has high surface tension, strong intermolecular attractions. We'll talk about hydrogen bonding in a bit with water. So that is to come. All right, here's where we're talking about our 3 types of intermolecular forces. So our first type that we're going to be looking at is our dispersion or London force, or London dispersion force, or London force. It's got a bunch of different names, but dispersion force, London force. These are our weakest intermolecular attractions. They cause instantaneous dipoles. We'll talk a little bit about that. And they're involved in every intermolecular attraction, including nonpolar molecules, including, I don't have it written down, but please write it on yours, non-bonding molecules. So let's think of like the noble gases. These happen in nonpolar molecules and in our noble gases. So you have at the bottom of your handout these little atoms of helium. So it says helium there. These are little atoms. Helium is number 2 on the periodic table. Its atomic number is 2, so that means it has 2 protons. And in neutral helium, which helium's neutral, it's got a full valence shell, we have 2 electrons. So that's what these little dots, I've colored mine a little bit, but that's what those little dots are. So we got 2 electrons floating around. Notice in this first picture, those 2 electrons are like basically in the middle of our atom. And they are zooming around each other, zooming around our atom, and here they are on polar opposites, but here, at any given moment, our electrons could be on the same side. So notice that to the left there where the electrons are, we have that little symbol for partial negative charge. Partial negative charges and partial positive charges go together when we have a dipole moment. We have more electrons on one side than we do another. So electrons have a negative charge. So over here we would have a partial negative charge because that's where all of our electrons are. And on the other side where we don't have electrons, we don't have negative charges, we're going to have a partial positive charge. So at any given moment, those electrons could be next to each other and we form these dipole-dipole charges. So let's think about that in terms of other 3 atoms. So this, we were talking about the same atom, just one atom that this could happen in. But if there was a helium atom next to this atom here, do you think that the electrons, the 2 electrons zooming around this helium nucleus, are going to want to be near those 2 electrons over there, that partial negative charge? No. They're going to jump away from that, but they are going to be attracted to this partial positive charge. So negative charges like positive charges. So let's consider that this atom here is this guy. We just moved it over. So our electrons have randomly zooming around and they ended up here, which means these 2 electrons are going to be attracted to this positive charge where there's no electrons, and they're going to jump over, which means that the atom, helium atom next to the other one, those electrons are going to jump over and be attracted to this partial positive charge. So these attractions, these London dispersion forces, are caused by these really, really small changes in where the electrons are, where our negative charge shows up. They are instantaneous, so they are super fleeting. They show up and leave in an instant because of where the electrons are constantly moving, orbiting our nucleus of our atoms, and so if they're constantly moving, that means these 2 electrons could jump around and we no longer have a partial negative charge here. Our partial positive charge goes away, which means that the next one goes away, the electrons are moving around, and then the next one goes away. So these are constantly happening, but they're super quick, super fleeting, which is why they are our weakest intermolecular attractions. So they're involved in nonpolar molecules, noble gases even, non-bonding. They're involved in every intermolecular interaction. Last thing on that page, our London forces are going to increase with increasing mass. So these cause increase in boiling point due to strong intermolecular forces, or stronger intermolecular forces. So let's think, for example, here we're talking about a helium atom. Helium atoms have 2 electrons. Let's look at xenon, number 54 on the periodic table, another noble gas. So here we have 2 electrons that are jumping over and that are being attracted to these charges. Do you think that the strength of the electrons jumping are going to increase if we have 54 electrons as opposed to 2? We have more guys jumping over to be attracted to these partial and positive and partial negative charges? Yeah, like that jump is going to be a lot stronger. So as we increase our mass, as we're going down the periodic table, we have stronger intermolecular forces with our London dispersion forces because we have more electrons that are jumping over. So if we have more electrons, stronger forces, that means that we need to get more energy into our system in order to go from a liquid to a gas. So that's our boiling point, going from a liquid to a gas. So lots of relationships that we need to remember there. Table 12.4 just gives us molar masses of gases and the boiling point. So notice as we're increasing our molar mass, going down the periodic table, we're increasing our boiling point because of London dispersion forces and those dipoles there. Okay, so example number 5. So I'm going to cover mine because I have the answer. Which halogen, chlorine or iodine, has the higher boiling point? So you basically can already see the answer, so we're just going to talk about it. Iodine. Iodine has the higher molar mass because it is lower down on the periodic table than chlorine. And if we have a higher molar mass, we're increasing our boiling point. So as we increase our molar mass, we're increasing our boiling point because we have stronger intermolecular forces due to the more atoms that are in our molecule and how big the atoms are. Okay, our next type of intermolecular attraction that we're going to be looking at are dipole-dipole forces. So these are stronger than our dispersion forces. They exist in polar molecules. So polar means we have an unequal sharing of electrons. So like covalent molecules, we're still sharing electrons, but one of our elements is more electronegative than the other. So it's going to have a stronger pull on those electrons. And then the strength of our dipole-dipole forces depend on the structure of our molecule and hence like what elements are there. So for example, fluorine is our most electronegative element. So if we have a molecule with fluorine in it, we're going to have a stronger dipole moment. We're looking at those electronegativity differences between the substances in our polar molecule. So as we're increasing our boiling point, an increase in molecular attraction causes an increase in boiling point. So if we have stronger intermolecular attractions, we're going to have a higher boiling point. All right, so here in this table, we have formaldehyde and ethane. So notice in formaldehyde, we have a carbon-oxygen bond. That is polar. But in our ethane, carbon-hydrogen bonds are non-polar. So we have an equal sharing of electrons here in ethane and unequal sharing in formaldehyde. So we have a polar molecule, and this little symbol is our dipole moment. So carbon has a partial positive charge, and oxygen has a partial negative charge. So let's look at our boiling point. So boiling point is higher for formaldehyde than it is for ethane because of the intermolecular force strength in our two molecules. So formaldehyde, because it's polar, we have dipole-dipole forces, and ethane, because it's non-polar, we only see London forces. All right, let's look at example number 6. Which of the following molecules have dipole-dipole forces? So let's look at letter A. So we need to do our electronegativity difference subtractions. So we are subtracting our bigger electronegativity value from our smaller one. So oxygen has a 3.5 electronegativity value. Carbon has 2.5. So if we subtract them, we get 1.0. That bond, that carbon-oxygen bond, is polar. But we also we also have to look at the structure of carbon dioxide. So carbon dioxide has a carbon in the middle and 2 oxygens around it, double bonded to it. So our molecular geometry for that would be MX2. We have no lone pairs of electrons on carbon. So we have a linear molecular geometry. So we have a linear molecular geometry. Do we also have the same atoms bonded to our central atom, to carbon? Yeah, we do. We have 2 oxygens. So if we have a molecular geometry of linear, trigonal planar, or tetrahedral, which we have linear, and we have the same atoms bonded to our central atom, even though we have a polar bond, we are a nonpolar molecule. So this guy is nonpolar because of symmetry. So we only have London forces there. All right, so let's look at, I'm just going to uncover that. CH2Cl2. So carbon is 2.5, chlorine has a 3.0, so that's a 0.5 electronegativity difference. We don't have the same atoms bonded to our central atom, even though we have a tetrahedral molecular geometry. Both conditions have to be met for a polar bond to be a nonpolar molecule. So we stay polar, and we have dipole-dipole forces. So letter B, we have dipole-dipole forces. Letter C, so CH4. So carbon-hydrogen bond is nonpolar, so 0.4 electronegativity difference. Nonpolar, therefore, we only see London forces. So letter B is the only one in example 6 where we're going to see dipole-dipole forces. Okay, let's look at our third and last type of intermolecular force that we're going to be looking at. Okay, hydrogen bonding. So hydrogen bonding, this is our strongest intermolecular force that we are going to see. These involve only a fluorine, oxygen, and nitrogen bonded to a hydrogen atom. So we have to have fluorine with a hydrogen attached to it, oxygen with a hydrogen attached to it, or nitrogen with a hydrogen attached to it in order for there to be hydrogen bonding. So a fluorine, oxygen, and nitrogen bonded to a hydrogen atom is polar. So this is a type of a polar bond, but because of the electronegativity differences, these guys are really strong. So it is a type of polar bond, but it's stronger because of these 3 guys bonded to our hydrogen. So these pictures here, like this guy, these lone pairs on oxygen are going to be attracted to these hydrogens, the partial positive charges of the hydrogens. So oxygen has a partial negative charge. So that partial negative and partial positive charge, those are going to be attracted to each other. So those are going to form hydrogen bonds there. Your DNA is held together in a double helix by hydrogen bonds. So they are very strong, and they're basically keeping us together and alive, which is kind of really cool. Okay, so let's look at ethanol and ethane. So here we have an oxygen bonded to a hydrogen. And look at our boiling point, 64.7 degrees Celsius. With ethane, though, we don't have any hydrogen bonds present. This is a nonpolar molecule, so we only see London forces. And we have a really low boiling point. So ethane's going to be a gas at room temperature. So hydrogen bonds, these cause high melting points and boiling points because they have strong intermolecular attractions. And they're going to be liquids at room temperature, so you do need to know that. Hydrogen bonds cause our substances to be liquids at room temperature. High boiling point, high melting points. All right, let's look at example number 7. Which of the following has the highest boiling point? Krypton, xenon, or radon? So this is going back to increasing molar mass and our boiling points. So that would be radon because it's lower down on the periodic table. It has a higher molar mass, hence the higher boiling point. All right, example number 8. Which of the following 2 substances is a liquid at room temperature? Which one and why? So I've drawn the structures here. So CH3O, CH3, those 3 hydrogens belong to that carbon. Those 3 hydrogens belong to the carbon. We have an oxygen in the middle. So just like this, with 2 lone pairs on oxygen. Notice how we don't have any hydrogens on this oxygen. So we don't have hydrogen bonding there. which means we're not going to be liquid at room temperature because hydrogen bonds cause they're liquids at room temperature. Here, CH3, CH2OH, we do have a hydrogen on that oxygen. So that means we do have hydrogen bonding there, and that's going to be a liquid at room temperature because of the hydrogen bonds. All right, so table 12.5 is basically just like a summary of our 3 intermolecular forces that we've seen. All right, I want you to try exercise number 9 through 14 on your own, and I want you to pause the video because I'm about to show you the answers, so I want you to see if you can figure them out. Okay, so here's our answers, 9 through 14. Which of the following compounds is a liquid at room temperature? Which one and why? So that's hydrogen peroxide because we have oxygen-hydrogen bonds. No hydrogen, so even though we have a fluorine, it's bonded to a carbon, so that's not a hydrogen bond, it has to be bonded to oxygen, and oxygen's bonded to a carbon, so we don't have a hydrogen bond there. Distinguish between intermolecular forces and intramolecular forces. Intermolecular forces, that's our definition that we first saw in the chapter handout. These are between molecules, 2 different molecules. And intramolecular forces are within a molecule. So one molecule, the forces in between them. So like electronegativity, like bonds and stuff like that we're going to look at there. Rank nitrogen, water, and hydrogen chloride in order of increasing strength of intermolecular forces. And what forces are present for each? Nitrogen would be our weakest, then we have hydrogen chloride, and then water. So nitrogen, the nitrogen-nitrogen bond is nonpolar, so we only see London forces in our nitrogen molecule. Hydrogen chloride, that hydrogen chlorine bond is polar, but chlorine is not one of our hydrogen bond guys. It's not nitrogen, oxygen, or fluorine. So that's just dipole-dipole. So it's still stronger than London forces here, but it's not as strong as water, the intermolecular forces between water molecules, because here with water we have a hydrogen-oxygen bond, which is a hydrogen bond, has hydrogen bonding capabilities. So water is our strongest. All right, number 12. Butane has a boiling point of 0.4 degrees Celsius, and hexane has a boiling point of 69 degrees Celsius, and explain. So we have a higher molar mass with hexane. There's a lot more carbons and hydrogens. So we're going to have stronger intermolecular forces and hence a higher boiling point because of that strength. All right, number 13. For which of the following compounds, if any, would hydrogen bonding be an important intermolecular force? So CH3, 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 NH2, and then H2S. So here in CH3, NH2, those 2 hydrogens belong to that nitrogen. That means we have 2 hydrogens attached to a nitrogen, and the nitrogen-hydrogen bond has hydrogen bonding capabilities. So we're looking for hydrogen bonding, nitrogen-hydrogen, oxygen-hydrogen, fluorine-hydrogen is what we're looking for there. All right, number 14. The normal boiling point of a substance depends on the molecular mass and on the type of intermolecular attractions. Rank the following compounds in order of increasing boiling points. H2SE, H2S, H2TE. So sulfur, selenium, and tellurium, they are right next to each other on the periodic table going vertically. So as we're going down, we're increasing our molar mass. Sulfur is the highest up, so it would have the weakest, the smaller molar mass, then selenium, and then tellurium. So that is those. All right, last thing we're going to talk about in this video is our types of crystals. So, our type of crystalline solids, my bad. So, solids typically form patterns, geometric patterns, when our molecules are bonded to each other. And we're going to describe those types of crystalline solid patterns. So we have molecular solids, ionic solids, and atomic solids. Molecular solids, so these are composed of molecules. So basically these are going to be 2 nonmetals or nonmetals bonded to each other, 2 different types of nonmetals. Our example here, dry ice, so that is just solid carbon dioxide. Carbon and oxygen are both nonmetals. And then ice, so hydrogen and oxygen are both nonmetals if they're bonded to each other. So that's our molecular solids are between two nonmetals, at least two. Ionic solids. So these are between a metal and a nonmetal. So salt and then calcium fluorine are our examples there. And then atomic solids, we're looking at one type of element that's bonded to itself, that we got forces that are holding it together, intermolecular forces that are just bonded to itself. So our first one that we're going to be looking at is a covalent. So these are between it's a nonmetal that's here. So diamonds are just carbon bonded to each other through intermolecular force bonds, strength, and in geometric patterns. So sulfur forms it in patterns of 8 as well. So carbon and sulfur are both nonmetals, so covalent atomic solids. Our noble gases are non-bonding atomic solids, so our example there is xenon. So non-bonding, we're typically going to see our noble gases. And then metallics, these are with our metals, so iron, titanium, any other metal that we're going to look at. Real quick, let's look at the melting points for all of these. Molecular solids, they have low melting points, relatively low melting points. Ice melts pretty easily. So like at room temperature, it's for sure going to melt. Ionic solids like table salt, they have really, really high melting points. So table salt, it takes a lot of energy to break apart that carbon, chlorine, those intermolecular forces in between our molecules. And then atomic solids, because we have 3 different types that we're looking at, our melting points vary. So that's why it says variable melting points. So let's look at example 15. Identify each of the following solids as molecular, ionic, or atomic. So SF6, we have sulfur, fluorine, both of those are nonmetals, 2 different nonmetals, so we're looking at molecular solid. Carbon is bonded to itself in patterns, so we're looking at one type of element, carbon, and then it's going to be covalent because carbon is a nonmetal. So atomic covalent solid there. Magnesium is a metal, chlorine is a nonmetal. So metal and nonmetal, those are ionic solids that we're looking at there. And then titanium is bonded to itself, and it's a metal, so we're looking at metallic atomic. Number 16, which of the following solids has the highest melting point? Why? So krypton solid, that is an atomic non-bonding. Sodium chloride, so salt, is a metal and a nonmetal, so that's ionic solid. And then we have hydrogen, oxygen, so that's nonmetal, nonmetal. So here we're looking at ionic solids. They have really high melting points. So that is why sodium chloride is your answer there. It's an ionic solid. They have really high melting points. All right, now you can do the worksheet titled Intermolecular Forces Worksheet. So you're putting into practice everything that we talked about in this video lecture.